Okay, so now we will move on to our next topic, which is mesh analysis, aka loop analysis. So mesh analysis is a technique for finding all branch currents in a circuit. All node voltages can be found if given resistances. Such technique is based on the principle of KVL, and as we know, KVL is based on conservation of potential energy. Such technique is also ideally suited for circuits that have mostly voltage sources, as you will see in examples. Direction of the loop current is also defined for each loop. KVL equations are written for each loop and mesh. Finally, unknown branch currents are found by solving a set of simultaneous linear equations. Now, let me first talk about the general procedure for mesh analysis, and we'll come back to revisit each of these steps. So number one, select m independent mesh currents such that at least one mesh current passes through each branch. Number two, define the direction for each mesh or loop current. Number three, write KVL equations for each loop or mesh. Finally, solve for all KVL equations simultaneously. For n equations, you can find n unknowns, and those unknowns are your mesh current or loop current. It is also important to note that for branches that are often common to two or more designated loops, the branch current equals to the net flow of the loop current incident on the branch. And this is something that I'm going to illustrate using our examples next. So example number one. So I have one voltage source here and another voltage source over here. There are altogether 1, 2, 3, 4, 5 resistors in this circuit. In this particular circuit's configuration, I have 3 separate loops. I have loop A, loop B, and loop C. In each loop, I'm going to designate first the direction of the current flow. This is exactly the same idea as we would do for KVL. In our KVL analysis, we have to specify the direction of the current flow. So I always use clockwise for the current or for the current direction. So in this case, I have 3 loop currents flowing in clockwise. So remember, we are going to use mesh analysis to find each loop current, IA, IB, and IC. And mesh analysis is based on KVL. So I'm going to have to use KVL for each of this loop. And based on the answers that I found for IA, IB, and IC, I can find unknowns such as IX, which is the current flowing through this 30 ohm resistor. And if I want, I can also use the information that I found from IA, IB, and IC to find the node voltage. For example, what is the voltage drop across this 20 ohm resistor? So this is going to be illustrated using this example. So let's begin with our first loop. So in loop A, this is my loop A, I'm going to perform a simple KVL over here. So I'm going to start on the bottom left, and I'm going to go clockwise. I'm going to go up to the right, down, and then to the left, back to the original starting point. So for loop A, if I go by this voltage rise, remember we can put all the voltage rises on one side and voltage drop on the other side. Okay. So for the first voltage, I have a voltage rise because this is my starting point and I'm going up, going from negative to positive. So I expect to have a voltage rise. So I put 12 volts on one side of the equal sign, and then I go to my next voltage drop. And the reason I know it's voltage drop is because I know the current is going clockwise. So when the current enters this 10 ohm resistor, it's going to create a plus here and a minus there. And since I'm going clockwise, I know I'm going from higher potential to a lower potential. So we know that this corresponds to a voltage drop. So then, since this is a voltage drop, so I'm going to put this voltage on the other side of the equal sign. So I have 10 times IA. I times R. That gives me this voltage drop. Okay. So again, on the left, I have voltage rise. On the right of the equal sign, I have my first term, and this corresponds to my first voltage drop. When the current is going clockwise, it's going to enter this 10 ohm resistor, creating a plus here and a minus there, which corresponds to the voltage drop. Okay, so now if I keep following this current flow, then now I see that the current is entering this 20 ohm resistor. So that is my current IA is going into this 20 ohm. But at the same time, this resistor is also shared by the neighboring loop or mesh. Okay. So in other words, this resistor is common to both IA and IB loops. Or you can say this 20 ohm is common to both IA and IB meshes. So in that case, if you look at this current IA, which is going down, and look at this IB, which is flowing up, this is going to create a net current flow, right? So when one is going down, when the other one is going up, right? Some of the current is going to cancel, right? So, and resulting in some net current flow. And this net current flow is assumed to be flowing in the direction of IA. So when I'm operating on loop A, I'm always assuming that IA is more dominant than anything else. When IA is flowing down and IB is flowing up, if IA is more dominant than IB, then I know IA is going to flow through this 20 ohm resistor. Or the net current is going to flow downwards through this 20 ohm resistor. So now if you go back to this steps, so we select n independent mesh currents, and we define the direction of each mesh, right? We assume that the direction is flowing clockwise, right? And we just started writing our first KVL equation for our first loop. Now, if you notice again, over here, I talk about the net flow of the loop current. Okay? And this net flow is the current that passes through this 20 ohm resistor, assuming that this loop current IA is more dominant than IB. Since IA is flowing down and IB is flowing up, so there has to be some net current flow going through this 20 ohm resistor. This net current flow is going to be coming from IA. So in that case, I'm going to take IA minus IB. So whatever the difference is my net current flow. And this will be dominated by this loop current, right? Since I'm operating loop A. So the net current flow, which is the delta between IA and IB, multiplied by 20 ohm resistor. So the current I times R is going to give me V. So then, as far as this loop is concerned, I have used KVL with voltage rises and voltage drop to complete my analysis for the first equation. So again, voltage rise and voltage drop and another voltage drop. And this voltage drop is equal to the net current flow, assuming IA is more dominant than IB, multiplied by 20 ohm resistor. Okay, so 3 elements, one here with 2 resistors. So I have 3 elements, and that will give me 3 terms, 1, 2, and 3. So this is my first equation, and we just have to repeat it 2 more times and solve for the unknown variables. So for loop B, so since I'm now operating on loop B, so IB is going to be more dominant than IA and IC. Okay. So in this case, again, I'm going to start from the bottom left. This is always my starting point, right? So now I'm operating on a new loop now. So IB, okay, so IB, so this 20 ohm resistor again is shared by these 2 loops. So now, assuming IB is more dominant than IA, so I need to find first my net current flow, so which is IB minus IA. So IB minus IA, the net current flow, multiplied by 20, I times R, that gives me voltage, plus because I'm using KVL, right, summation, plus IB times 30 plus Vy, where Vy is equal to IB minus IC. Again, IB is more dominant than IC, right? So the net current flow is going to be flowing in the direction of IB. So this net current flow is going to flow downward through this 20 ohm resistor. So IB minus IC times 20 ohm resistor here, which is equal to Vy. Okay. And now you sum all this to 0, and this is your second equation. The last loop or last mesh, do the same thing. We start from here. So IC minus IB times 20, right? So when I'm operating on IC loop, I'm assuming IC is more dominant than IB. So the net current flow is now going to flow up, right? Because I start from here, IC goes up, but IB is flowing downward. They are flowing in 2 opposite directions. But since I'm operating on loop IC, I'm assuming IC is more dominant than IB. So therefore, the net current flow is going to follow the direction of this IC current. It's flowing upward. So IC minus IB times 20, the net current flow multiplied by 20 is going to be to the voltage. Summation, right? KVL, so plus 6 volts plus 20 times IC. Right? This one is easy because this 20 ohm resistor is not shared or common to another loop. Right? This is by itself. So the only current that passes through this 20 ohm is IC only. So 20 times IC. Sum all these voltages up to 0, and this is your third equation. So now you have 3 equations and you have 3 unknowns, and those unknowns are IA, IB, and IC. So go ahead and solve for those unknowns. Did it here for you. So IA is 0.47 amp, IB is 0.11, and IC is minus 0.096. So then the question is, what is IX? Okay. So IX by inspection, right? So if you look at where IX is flowing, this IX is flowing through this 30 ohm resistor, which is the same as this IB current, right? Because IB is also flowing through this 30 ohm. So we can say that IX and IB are the same. So IX is therefore equal to 0.11 amp. Once you know IB and IC, or once you know IA, IB, and IC, right, you can find pretty much all the node voltages that you want. Right? So for example, in this case, Vy is the voltage drop across this 20 ohm resistor, which is this voltage here. The voltage between this node and this node. And we know this node here, right? Even though I didn't put my ground reference here, but we know that there exists a ground reference here. If you want, you can put a reference here. A ground reference, 0 volts, right? So that means this node here is my ground. So the voltage between this point and ground is my Vy. And this is nothing but the current passing through this 20 ohm resistor times 20 ohm. Right, I times R. So what is the current I? I is equal to, over here, right, the net current flow, IB minus IC. IB minus IC is going to give you, is going to create a current flowing downward. That's going to create a voltage drop with plus here and minus there. Current goes into plus first and leaves the minus. So in this case, Vy is equal to IB minus IC times 20. So IB minus IC, if you will, you can call this IY. And IY is the current passing through this 20 ohm resistor, which creates my Vy. So this is equal to 4.12 volts. Okay, so another thing that you can use to visualize this is this. So IB is the current that flows into this node. IC is the current that leaves this node. Right? So this node here is this node. Okay. So IB is going into this node. IC is leaving this node. So to figure out IY, right? To figure out IY, you know this is simply, right? I can use simple KCL, where IB going into the node has to be equal to the current leaving the node. IB is going into the node, entering the node, and the sum of IC and IY leaving the node. So IB therefore is equal to IC plus IY. Right? So you can use this to figure out what your IY is. Okay, so IB is equal to IC plus IY. Solve for IY, and you will get IB minus IC. It's the same as what we over here. This is based on this net current flow. Okay, so let's look at our next example. So in this example, again, I have 3 loops, and I'm going to call it I1, I2, and I3. So I'm still going to use the mesh analysis based on KVL. Okay. So I'm going to first look at this I1 loop. And for this I1 loop, again, I'm going to follow this clockwise direction to find what is I1. Okay. But it turns out that for this particular loop, there is not much you need to do. Right? Because if you remember, the objective here is to find what loop current is. Right? Current corresponding to each loop, I1, I2, and I3. But for this loop 1, the current is already given to you. Right? Because as you can see, I have this current source flowing or inserted in this loop. And this current is going up this way. This is my 2M. So I1 is also flowing upward. Right? So I1 therefore is simply equal to 2M. Okay, so this is something that you can just eyeball, by inspection, you can figure out what I1 is. So I1 is equal to 2M. Perfect. The next loop, I2, we're going to start from here, just like before. So for I2 loop, I have I2 minus I1 times 10. I2 minus I1 is my net current flow, and this net current flow is going to follow the direction of this I2 current. So I2 minus I1, the net current flow multiplied by 10, plus summation plus I2 times 5, right? So I'm still going clockwise, right? So now I'm over here. The current is now going through this 5 ohm resistor. So I2 times 5 plus, so again, this 20 ohm resistor is common to both I2 and I3 loop. So I need to find the net current flow. So that is I2 minus I3 times 20. Sum all of this to 0. Right, so I have 3 terms because I have 3 elements, 1, 2, and 3. Loop number 3, right? Let's repeat it one more time. I'm going to start from here. I3 minus I2, assuming I3 is more dominant than I2. So I3 is imposing. Okay. So I3 minus I2 times 20 plus 2 times I3 plus 8. Sum all these terms equal to 0. Okay, so that's my equation number 3. So based on these 3 equations, you can figure out I2 and I3, right? Since I1 is already done by inspection. And notice that for this loop analysis, you don't have to always use clockwise for the current, or for the direction of current, right? If you want, you can also use counterclockwise, right? I use clockwise just because this is my personal preference, right? When we talk about KVL, always started from the bottom left, and then I go clockwise. But you don't have to, right? You can do counterclockwise if you want, but you just have to keep track. You just have to be consistent, right? And similarly, if you don't like to start from the bottom left, you can also start from the bottom right, okay? Or top left or top right. The only thing that you have to make sure is you start at this point and you have to end at the same point so that you complete the loop. Okay, if you start here, for example, if you start on the top right and you end up over here, then that's not good because you will be missing out this 10 ohm resistor. Okay, so the loop is incomplete. So you're going to have missing terms in your equation. Then the answer will be wrong. Next example. So again, I have 3 loops, and I have 3 voltage sources. And for this question, you're asked to find not just I1, I2, and I3, but also what is the current passing through this 2K ohm, and also the voltage drop across this 1K ohm resistor. So again, I'd like to start from my loop 1 here. So loop 1, I define my loop, current, loop 1, loop 2, and loop 3 this way. I'm going to start with the first loop, and I'm going to start again from the bottom left and going clockwise. So go up to the right, down, and then to the left. And since this is kind of new to you, so my suggestion will be for you to trace out this loop completely, right? So sometimes when you have done this several times, right? So you tend to be a little more sloppy when you indicate the direction of the current flow, right? So sometimes you'll see that I just do something like this, right? But perhaps for now, it will make sense for you to do it this way. So you make sure that this is still going clockwise, but you throw it out this way such that you don't miss any element. As if you just draw like a circle like this, right? Even though this is going clockwise, right? Sometimes you may overlook and you may miss one of these elements along the way. Okay, so when you sketch this one out this way completely, right? Then you see that these lines, this path goes through the element. We'll miss it. Okay, so for our first loop, I have 10 volts. Okay, so 10 volts is my voltage rise. Now, of course, if you don't like this idea of voltage rise and voltage drop, that's fine. You don't have to follow this. So another way of doing exactly the same thing, okay, or equivalently, is remember, if I start from here, I keep track of the sign, right? So the first sign that I see is minus, it's negative, right? So I'm going to do minus 10, okay? So I'm going to remove this 10 over here, right? I'm going to put it 0, so minus 10, okay? Plus I1 minus I2 times 5K is this guy, okay? So I'm going to do plus. The algebraic sum of all the voltages around the loop has to be equal to 0, right? So that's the definition I'm using. So minus 10 plus I1 minus I2 times 5K plus, now I'm over here, right? So this 1K ohm resistor is shared between I1 and I3 loop. So 1K times I1 minus I3, assuming I1 is more dominant because I'm operating on loop 1. Okay, and this is my equation. So now you see that if I move this minus 10 to the other side, then it will be exactly the same as what I originally had, right? So 10 is equal to this thing. Okay, so it's up to you which way you want to use. Okay? Eventually, they are the same mathematically. So for loop 2, this guy over here. So again, I'm going to start from, let's say let's go from here. Okay. I'm going to trace this one out this way. With 4 arrows, right? Up to the right, down to the left. It's like this. So what I have here, if I start from here, okay, so I don't have anything here, so I need to keep going to the right. So I2 times 10K, so over here. So I2 times 10K. Keep going to the right, I don't see anything. I keep going down, okay, following the path, I don't see anything. But now I'm going to the left, so now I see something, I see this 2K. But we know that this 2K is shared between I2 and I3, so I know I need to take I2 minus I3 bracket times 2K. Okay. Plus, right, summation, I'm using KVL, so plus negative 20. Why negative? Well, because if you look at the sign, this is minus. So plus minus 20, or simply just minus 20 in the notes. Keep going to the left, okay. I see this 5K. So 5K is shared between I1 loop and I2 loop. So what do I have? I2 minus I1 times 5K, which is this term over here. Okay, I start from here, I go around the loop, I have 1, 2, 3, 4, 4 elements, including this voltage source. So I have 4 terms, 1, 2, 3, 4. Summation using KVL to 0. Second equation. Loop number 3. This is my starting point. So clockwise, up to the right, down to the left. When I go up, I see this 1K ohm. Okay, so this 1K ohm is shared between I3 and I1. So I3 is going to be assumed more dominant than I1. So I3 minus I1, creating a net current flow going upward through this 1K ohm. I3 minus I1 times 1K. Plus summation, right? 20 ohm, because I see plus sign first, so 20. Plus 2K times I3 minus I2. Again, I3 is more dominant than I2 because I'm operating on I3 loop. Plus 4K times I3. Now, this one is easy because 4K is not shared between I2 and I3. Okay. By the time current goes downward, right, this 4K only sees I3. So I3 flows down or through this 4K ohm resistor. So 4K times I3. Simple. Plus negative 2. Negative because I see negative first. Minus sign, the negative terminal of this voltage source. Minus 2, sum everything up to 0. As a sanity check, you can check how many elements you have passed through. 1, 2, 3, 4, 5. Therefore, there should be 5 terms. 1, 2, 3, 4, and 5. Sum to 0. Okay. 3 equations, 3 unknowns, and they are I1, 2, and 3. So for I1, I2, and I3. Okay. And assuming we have done that, let's find what Vy is. So Vy is equal to Iy, which is the current passing through this 1K ohm times 1K ohm. Okay. And what is this current IY passing through this 1K ohm? Well, by the same token, I have a small workout or notes on the right over here. So you see that as far as this node is concerned, right? So if I put dot here, this dot is this dot. Okay. Current I1 is entering this dot. Current I1 is entering this dot. Current I3 is leaving this dot. Current I3 is leaving this dot. Current IY, which I call, right? Current IY is the current flowing through this 1K, is going downwards, okay? It's going downwards, right? And I need to know this current so that I can take this current multiplied by 1K to find my Vy, where Vy is the voltage drop between this point and my ground, right? So I have this ground over here, and this is my ground, this is my ground. It's the same ground, right? So you don't have to draw this ground symbol 3 times, right? Actually, 1 time is good enough. Okay, but I'm just doing this to show you that this is ground, this is ground, this is ground, and this is my common ground. Okay. So IY, what is IY here? Right, using KCL, right? This little side exercise on the side, right? Using KCL, current entering the node is equal to current leaving the node. So I1 is equal to IY plus I3. I1 is equal to IY plus I3. Therefore, IY is equal to I1 minus I3. Okay, and which simply is just the net current flow going down this way. And this net current flow we know is I1 minus I3. Right? If you know how to do this by inspection, right, you can probably skip this little exercise on the right here. Okay, so I have IY, which is I1 minus I3. Take that current multiplied by 1K, I will get my Vy. Now, similarly for Ix, where's Ix? Ix is the current entering this node. Probably use different color here. Color. Use red here, red here. Okay, so Ix is the current entering this node. Right, I'm just cutting out this part of the circuit diagram and paste it over here for our analysis. So Ix is entering this node. I2 is also entering this node. And where is I2? I2, remember, I2 is this loop current. So and this loop current goes like this, clockwise direction, right? And by the time it goes down, right, it goes down here, right, it's going to enter this node. Right? So I know this current is also I2. I3 current is the current that leaves this node, right, going downward this way, right? So this loop current, I3, like this. So what is Ix? Well, simply you use KCL again, right? So KCL says the current entering the node has to be equal to the current leaving the node. Current entering the node is I2 plus Ix. Current leaving the node is I3. Okay, so based on the relationship, we know Ix is equal to I3 minus I2. Right? So I take I3 minus I2, that gives me minus 3.5 milliamp. Interestingly enough, Ix is a negative number. And what does that tell you? Well, I assume that Ix flowing from left to right or I assume this current going from left to right is my Ix. Okay, but this Ix turns out to be minus. So that means if I change the direction of this current, if I reverse the direction of this current, so if I draw it like this, okay, this current is going to be 3.47. Take the unit here, milliamp. Okay. If Ix going from left to right is minus 3.47, then the current going from right to left will be positive 3.47. Okay, that's just the way the current direction is flipped or is reversed. Right. So I have a negative of what this Ix is flowing. Okay, so it turns out to be minus 3.47 for Ix, and which is fine. Okay, this just means I'm off by a negative sign. I assume the direction is flowing in the opposite direction as my positive current in the first place. Okay, so now let's move on to talk about a more advanced technique called super mesh. Okay, so super mesh is the dual of super node. So if you remember, for super nodes, there exists a floating voltage source that is difficult to deal with. Okay, so we have to use slightly different technique, okay, to solve for the nodal analysis. Similarly, for mesh analysis, if you have a situation like this, so let's look at this circuit a little bit detail. So for whatever reasons, if there exists a current source stuck in between these two loops, or for whatever reason, I have this current source that is common to both these two loops, then unfortunately, I cannot clearly define the voltage drop across this current source, right? If you remember, this mesh analysis is purely based on KVL. And for you to write your KVL equation, you need to know the node voltage, right? KVL, the summation, the algebraic sum of the voltages around the loop, right? But let's just say if there's no way for you to define this voltage across a certain element, and that element is this current source, then you're not going to be able to complete your KVL equation, right? Because KVL relies on your voltages, right, around your loop. But if this voltage across the current source is undefined, then there is no way for you to complete the loop. Okay, so that's basically the underlying problem. Okay, so we use super mesh analysis when an independent or dependent current source is common, right? So this current source is common to two or more loops. I'm using two loops as an example, right? But of course, this guy can be common to more than two loops, okay? So I have two loops here. This guy is sitting right in the middle and is common or is shared by these two loops. Okay? And this is analogous to floating voltage source in the nodal analysis. Okay, so again, the problem statement here is we cannot define the voltage drop across this current source. Okay, so therefore we have to, come up with something else, and that something else is what we call super mesh. So super mesh says that, well, I can still do my mesh analysis, but I just have to avoid, okay, this branch that contains the current source. And we are going to end up with a similar situation like super node analysis, right? So in the super nodal analysis, remember we need to have another equation to relate between two voltages, right? So that we can solve for all the unknowns, right? Otherwise, we'll be missing one. right? So exactly the same idea here. We need to come up with that equation relating I1 and I2. Okay, so I need to write another equation that at least describes the relationship between I1 and I2 such that I can go ahead and solve for the two unknowns with two equations still. Okay. The current source defines the relationship between the adjacent mesh currents. That's how you will come up with that second equation. So in this case, it's very simple, right? So how do you relate this current I1 and I2, even this current source sitting in between? Well, this is exactly what we just saw. Put a note here. And we have current flowing into this node, which is I1. Current flowing out of this node, which is I2. Current flowing into this node, right, which is set by the direction of this current source, which is Ix. Using KCL, I have current flowing into the node, which is I1 plus Ix. And the current leaving the node is I2, right? So I can relate I1 and I2 now, right? So simply I2 is equal to I1 plus Ix. Current entering the node is equal to current leaving the node. So this will be one important equation that you need to have so that you can solve for I1 and I2. Okay, two equations, two unknowns. Okay, so I'm going to show you two examples illustrating super mesh. And of course, I'm going to rotate this page. I like to go clockwise, usual. Okay. First example, I have a couple of voltage sources, one here and one there. I have this current source, which is right just like what we said. This guy here is common to two loops. And this guy here is stuck in between these two loops. So I know somehow I have to use slightly different technique to get around this problem. Okay, so let's look at the external loops first. Okay, so I have IA and ID. Okay, and I'm going to go ahead and also assign IB and IC over here, right? So even though I know I'm going to use super mesh, right, and I can consider this as my big loop, right? But still, I like to assign IA, IB, IC, and ID, right? Because it's obvious that we have four loops. Okay, 1, 2, 3, 4. Okay, IA, IB, IC, ID, and I'm going to start with IA. Okay, so loop IA, this is my starting point going clockwise. So I'm going to put, instead of -20, right, I'm just going to move that -20 to the other side, so 20 volts over here. Okay, done this. I've seen enough examples, so I'm just going to do this in one step. So I move -20 to the other side of the equal sign, so I have 20. 20 volts, this is equal to IA times 5, first term, plus IA minus IB times 15. Right, this one here is easy, right? Because we know how to do this already. We just need to find the net current flow, which is IA minus IB, assuming IA is more dominant. IA minus IB, net current flow downward through this 15 ohm resistor times 15, I times R. This is my first equation. Now, I can go to IB, loop IB, okay? But we know that if we go to loop IB, right? So let's just, for the fun of it, let's just try this one out. So if I start from here, I can do IB minus IA times 15, no problem. This one is easy. IB times 20, no problem. But by the time I go to this point, I go through this current source, right? And I need to find the corresponding voltage drop across this current source. I'm going to have problem there, right? Because just like I alluded to you earlier, the voltage drop across this current source is undefined, right? If I want to use KVL, I need to know the voltage drop. Okay. Unless I replace this current source with a resistor, there's no way for me to find the voltage drop. Now, if I replace this guy with a resistor, then I can just carry out the analysis like before. If I have a resistor here, I can do IB minus IC times whatever this resistor is. Right? Just like this 15 ohm resistor. You do IB minus IA times 15. Right? But in this case, I don't have a resistor there. I have 3M. Okay. So then I'm going to have to use super mesh. And this super mesh, okay, works like this. You will still find the voltage drop across this 15 ohm, this 20 ohm, okay? But you are going to bypass this current source. You are going to move on to the neighboring loop, to the next loop, which is IC, right? Because you know that this current source is common to both IB and IC. So now my super mesh consists of IB and IC, not just IB or IC. This super mesh consists of IB loop and IC loop. So now I'm going to have to extend my loop a little bit more. So my starting point is still on the bottom left. So I go up, passing through this 50 ohm, part of the loop, passing through this 20 ohm, part of the loop, go all the way to the right, right? Because I know I cannot go here, right? This path here is undefined, right? I don't have a defined voltage drop here. So I have to go to the right. I go down, creating another voltage drop, and I go to the left, back to the starting point. So this is now my new loop for the super mesh. This loop consists of IB and IC loop. Okay. So again, starting from here again, I have IB minus IA times 15 plus 20 times IB, voltage drop, plus, skip this one, but I go all the way to the right. I go down. So going down, I have this 10 ohm resistor shared between IC and ID loop. So this one I can do, right? Because I can take IC minus ID times 10. That's what I have over here. Then equal to 0, summation to 0, KVL. And of course, you're going to wonder what we are going to do with this one. So jumping ahead, I'm going to go to equation number 4 first. IC is flowing into this node. IB is flowing into this node. IC is leaving the node. This current, which is 3M, flowing downwards, is also leaving the node. So I remember I need to come up with one more equation that relates IB and IC together. So this is that equation we're talking about, right? So current entering the node, which is IB, current leaving the node is 3 plus IC. So IB is equal to IC plus 3. This is my fourth equation. Okay. So now going back to loop B, which is this one, right? This is the external loop to my super mesh. So this one is easy. So I start from here. I go up, right? So I have ID minus IC times 10 plus 12 plus ID times 30. Okay. 1, 2, and 3, 3 terms, right? 3 elements, 1, 2, and 3. Summation, set it to 0. This is my last equation. 4 equations, 4 unknowns, IA, B, C, and D. Go ahead and solve for these unknown variables. Once you have these unknown variables solved, you can find Ix and Vy easily. Right? So what is Ix? Well, Ix by inspection, Ix is the current flow flowing through this 20 ohm resistor, and which is the same as IB, because IB is also flowing through this 20 ohm. So Ix and IB are the same. Okay. What's Vy? Well, remember, Vy is equal to some Iy times this resistor. So how do you find Iy? Right, using KCL here at this node. Iy simply is equal to ID minus IC. Let me just make sure I got it right. IC equal to Iy plus ID. So Iy is equal to D minus ID. Okay, I think I just misspoke. So this one is correct. Iy is equal to IC minus ID instead of ID minus IC. Following this. Okay, so you have Iy and you have this resistor, and you take that resistance times current, and you will get the voltage. Right? Simple Ohm's law. Okay. All right, so let's move on to our last example. Okay, so now let's move on to our last example. So again, we'll be using super mesh for this problem. Okay. So clearly we have 3 loops. I'm going to call it IA, IB, and IC. And notice that this current source is common between IA and IB. And this current source is not an independent current source. Instead, it's a dependent current source. Depends on this Vy voltage, and this Vy voltage is over here. So remember, we talked about this type of current source, right, with diamond shape. This is a dependent current source. And this is, in this case, I have a voltage control current source. This current is controlled by this voltage Vy. And this Vy exists over here in this part of the circuit. All right, so since I have this current shared between these 2 loops, so I'm going to have to use super mesh. So again, I start from the bottom left, and I sketch out this entire super mesh path. So 2K times IA, 2K times IA minus 12 volts, right? I know 12 because this is negative first, plus IB, right? So I'm going clockwise, so plus IB times 8K, going down, plus IB minus IC times 1K, right? I'm assuming IB is more dominant than IC, right? So IB minus IC is the net current flowing through this 1K ohm. And this is sum to 0. And notice that I'm bypassing this current source, right? Because I know that this is the current source, and I don't have an easy way to define the voltage across this current source. This 3 times Vy is not voltage. This 3 times Vy is indicating this current, the current associated with this dependent current source. Okay. So I have to go this way clockwise, all the way to the right, down to the left, bypassing this current source. But of course, we know we will need to come up with another equation that relates IA and IB, right? So that we can solve for, so that we have 3 equations and 3 unknowns to solve for IA, IB, and IC. Okay, so we'll come back to that in a second. So, so let's look at IC first, loop IC. So IC minus IB times 1K, I'm going clockwise, plus IC times 5K, which is guy, plus 7R, 7 times IR. 7 times IR is this current control voltage source. So this is the voltage source in a diamond shape, the dependent voltage source, and it's controlled by current. That's by this IR. And where's IR? IR is the current flowing through this 1K ohm. Okay. So if you will, this is my equation 1, this is equation 2. Now I'm gonna need to have another equation, right? Just like I mentioned. And this equation has to relate IA and IB together. Okay. So how do I do that? Well, similarly, I'm going to write a simple KCL over here, right? Because this is the node that is shared by all these 3 different branches. Okay. So this current going down is 3 times Vy. Current entering this node is IA. Current leaving the node is IB. Okay. So 3 Vy is equal to this current IA minus IB. Okay. If you don't see this immediately, you can also do it this way. You can say current going into the node, this node, okay, is equal to current leaving the node. Okay. So based on this, you can figure out what 3 Vy is. So 3 Vy is IA minus IB, right? Move IB to the other side, so you got this. Okay. And we also know that Vy, this is Vy, is nothing but IB times 8K. IB is the current passing through this 8K ohm. Okay, so Vy times 8K. Sorry, Vy is equal to 8K times IB. From these 2 equations, you can figure out IA. So IA is equal to 3 times 8K times IB plus IB. Okay. What's IR? IR is simply, right, again, using KCL at this node, IR is simply IB minus IC. So with all these equations here, you can figure out all the unknown variables, including IA, IB, IC, Vy. Okay, Vy, which is this guy, right? Once you know IB, you know Vy. And IR. The IR is the difference between IB and IC. Once you know IB and IC, this one is easy.